Hey everyone, and welcome. Today, we're going to break down something that's absolutely fundamental to marine automation, the simple 0 to 10 volt signal. We're going to see exactly why this signal is such a huge part of a massive ship's complex nervous system.
So, let's start with a puzzle. Picture yourself on the bridge of a gigantic ship. You need to tweak a valve way down in the engine room, maybe a whole kilometer of steel and cables away. How in the world do you send a command that's not only instant, but also super precise? That's the problem we're going to solve today.
You know, modern ships are basically floating cities. They have thousands of parts that all have to work together perfectly. And to do that, they need a super reliable nervous system, a way to send out commands and get feedback in the blink of an eye. And that entire system is built on a language of electrical signals.
Now, in the world of marine automation, controllers and sensors speak two main analog languages. You've got your 4 to 20 milliamp current signals, and you've got your 0 to 10 volt DC voltage signals. Today, we're going to zero in on that second one, the surprisingly powerful and straightforward language of voltage.
So, how can something as simple as voltage act like a language? Well, it's all about direct, proportional communication. It's a crystal clear, no-nonsense way for one piece of gear to give an order to another.
At its heart, a 0 to 10 volt signal is just beautiful in its simplicity. The amount of voltage you send is directly proportional to the message you're sending. Seriously, just think of it like a dimmer switch for a light in your house. Turn the knob a little, you get a little light. Crank it all the way up, and you get full brightness. It's that intuitive. And this direct relationship is everything. If a controller sends out 0 volts, it means minimum. Hey, turn off, or close this valve completely. If it sends out 10 volts, that means maximum. Go to full power, open that valve all the way. And most importantly, if it sends 5 volts, it means exactly 50%. Every little step in between is a precise, understandable command.
So you might be wondering, why has this incredibly simple signal become so popular on these complex, high-tech ships? Well, its simplicity is actually its greatest strength. Let's dig into the advantages.
First off, it's super easy for the ship's electronic brains, the PLCs, or programmable logic controllers, to generate and understand. Second, it's fast, like really fast. And that quick reaction time is perfect for things that need smooth, continuous adjustments, not clunky, jerky movements. And finally, electronics just get voltage. It's their native language, so processing it is a piece of cake.
And this is where that speed and simplicity are mission critical. We're talking about the big stuff, controlling the engine's speed, managing the flow of fuel, and even running the ship's massive air conditioning systems. These are places where you just can't afford any delays or mixed signals.
But it's not all smooth sailing. I mean, think about it. The ship itself, this huge metal box packed with powerful machinery, creates a really harsh environment for a delicate electrical signal to travel through.
The two biggest enemies of our voltage signal are electrical noise and voltage drop. All those huge motors, generators, and thick power cables running everywhere create a ton of electromagnetic interference, or noise, which can mess with the signal. And just like water pressure getting weaker at the end of a really long hose, voltage can literally drop as it travels down a long cable, making the signal weaker.
Okay, here's a perfect example of what that means. A controller sends a command for 90% power. So it sends out a clean 9-volt signal. But over a long and noisy cable run, that signal gets weaker. By the time it finally arrives at its destination, it's only 8.5 volts. Now the equipment thinks the command was for 85% power. That's a huge error that could cause some serious problems.
So, with these weaknesses, what's the solution? Well, the answer isn't to just ditch the 0 to 10 volt signal. The answer is to be smart and use the right tool for the right job.
For any task where accuracy over a long distance is the absolute top priority, like getting a temperature or pressure reading from a sensor far away, engineers turn to that other language we mentioned at the start, the 4 to 20 milliamp current signal. It's just way more resistant to noise, and it doesn't suffer from that pesky voltage drop.
And this right here, this brings us to the biggest takeaway of the day. It's so important. The 0 to 10 volt signal is best for control. It's for telling a valve actuator or a pump what to do. It's simple, it's fast, it's perfect for giving commands. On the other hand, the 4 to 20 milliamp signal is best for measurement. It's for listening to what a sensor is reporting, because it's tough, reliable, and accurate over those long distances.
If you're a student, a technician, or just curious, this is the one sentence to tattoo on your brain. This is the golden rule that governs so much of how these incredible systems are designed. One signal is for listening, the other one is for talking.
So after all that, what is the one key idea you should walk away with?
It's this. In the real world, out on the water, you have to understand both of these languages. When a system goes down, knowing whether you should be looking for a voltage command or a current signal from a sensor, well, that's the key to figuring out the problem fast and keeping these incredibly complex machines sailing safely around the globe.